Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts project at thunderbolts.info.
One of the most important discoveries of the space age has been the detection of vast networks of filaments which connect celestial objects across all scales in the cosmos. From the filamentary networks along which stars form, to the so-called cosmic web, or Catherine wheel-like form of galaxies linked by colossal filaments, and even plasma filaments which connect superclusters across unfathomable cosmic distances, and which have been found to be both magnetized and to emit electromagnetic radiation. In a previous 4-part series on space news, physicist Eugene Bagashov explored the role of Birkeland currents within the Milky Way galaxy and close to our solar system. Eugene discussed the evidence he and his colleagues, including Jim Wenninger, had uncovered that the local interstellar chimney, where our solar system is situated, may represent a giant plasma filament. He also explored the question, might Birkeland currents within our solar system play a role in catastrophic planetary events, both in the past and potentially in the future? Another member of the Electric Universe community who has investigated these questions is Gareth from the YouTube channel See the Pattern. Gareth has offered remarkable, prolific analysis on many fundamental issues for the Electric Universe and plasma cosmology. In this episode, Gareth introduces his investigation into a remarkable evidentiary connection between the Birkeland currents in our celestial neighborhood and a possible cycle to cosmic catastrophe. To understand this linkage, Gareth offers a groundbreaking analysis on the celestial phenomenon known as the Precession cycle. To view Gareth's YouTube channel, visit the link in the description box of this video.
Most people are aware of the notion of precession. It is often referenced in many New Age paradigms about the coming of cyclic disasters. The mainstream has very fixed ideas of what precession is. What if this was completely wrong? What if the cause of precession was far simpler, and hidden within this simplicity lies a fundamental truth about our local neighborhood? Observations have shown that the sun rises in different constellations on the solstice each year throughout history. It is believed that this cycle takes about 26,000 years to complete one full circle. It was first discussed by Hipparchus in about 150 BC. He used older data of the star Spica and determined that it had moved 2 degrees relative to the autumnal equinox. He concluded that the equinoxes were moving. Unfortunately, most of his writings have been lost. There is, however, mention by Ptolemy, who explained precession as the rotation of the celestial sphere. There are also claims that the Mayans' long year count of 30,000 years, involving the Pleiades, may have been an effort to calculate the precession of the equinoxes. There is also some evidence that Egyptians were aware of this movement. There is clear evidence that the Indian astrologers were aware of precession. In the most recent translation of these texts, they derive a period of 25,461 years. It was Copernicus who first suggested that this movement of the equinoxes might be due to the Earth's spin axis wobbling. It was Newton who then assigned gravity as the cause of this. To date, there is no evidence that any of the axes are wobbling with respect to any solar system objects, but we do see this with the stars. His initial equations never matched the actual precession rate, and so a long series of tweaks were initiated by many different people to attempt to bring this value back in line with observations. But none ever questioned the underlying assumptions. The first law of physics any of us humans learn, we learn before we are old enough to read or even talk. Unfortunately, our intuition tricks us into believing it is simply a downward force. By the time we go to school and learn that gravity acts between masses, it is too late, and the damage is done. And even Isaac Newton fell victim to this delusion. Most of you may have seen or used a gyroscope. Spin it up and you can easily balance it on your finger. Move your hand slightly to the side and the gyroscope will start to precess. and this means that the gyroscope's top axis wobbles in a circular motion while the bottom axis remains fixed. The problem with this setup is that when we examine the forces involved, it requires one important thing: the force of gravity to be acting downwards. If we remove this condition, something totally different happens. As we can see, no precession is set up at all. As time went by, observations started to appear which indicated that something other than precession was happening. Let's examine some of the problems for precession. Number 1. If you examine the equations that are used to calculate this, you will see that they are based on a mathematical formula, not on the mechanics of how the solar system works. This formula only works when the start is pinned at a very specific date and is only accurate for shorter time frames. As time goes by, it will no longer match the observations, and in fact the time for each cycle is getting larger and larger, causing them to have to tweak this formula to account for this discrepancy. Number 2. When we observe the motion of the stars relative to the Earth, we see that the Earth itself does not complete a full rotation equinox to equinox. Instead, it completes only 359 degrees, 59 minutes and 10 seconds, equinox to equinox. This is not true if you measure the movement of the equinox relative to the Sun or the Moon or other objects within the solar system, where the lunar data shows us that the Earth goes around the Sun a complete 360 degrees in a tropical year. So we are back to the problem that this does not show that the Earth wobbles. Number 3. Homan was interested in why the Egyptians used Sirius to mark their calendar. He discovered that Sirius rises with the Sun the same day each year. He did transit timings of Sirius and found that it moved at a rate that kept it from precessing. Or should I say, from precessing along with the other stars. In other words, it seemed to be stationary compared to the moving stars year on year. So here is the question: how can a star moving in a straight line across the sky keep in sync with rotation about an axis for long periods of time? It can't happen. That star would have to circle that same axis. This was the puzzle that Jim Wenninger stumbled across before he found the electric universe. Cruttenden and Homan were convinced that this was evidence that Sirius was circling us. They wanted to make it our binary companion in a gravity-only model. Jim Wenninger's first realization was that there was no way to orbit an axis rather than the center of mass. We appeared to be circling the same axis, but not the same center of mass. They stuck with the gravity-only binary idea, and he was stumped until he found the EU. In a gravity-only model, there simply was no way for these two stars to orbit an axis further out. There simply wasn't enough mass to do this. When Jim started to investigate the electric universe, he discovered that there was an alternative mechanism which would allow stars to orbit a common axis rather than requiring gravity. His first clue came when he examined the Helix Nebula. When he stumbled onto the mainstream estimates for the spiraling around the double helix nebula, it was the same order of magnitude as our precession, and he knew he was onto something. If we examine our local neighbourhood, we see Alpha Centauri sits about 4 light-years away from us, and appears to be situated across from us on the other side of a large gas cloud. In between us there does appear to be a large void. If we examine the motion of Alpha Centauri, we also see it has a much higher tangential velocity compared to other stars. This is what we would expect if this was on the opposite side of a twisting filament. Sirius seems to sit a little further back, on the same side as Alpha Centauri. Could it be that these clouds are in fact filaments, and are part of a much larger filament? Moving a little further out, we see that the Sun sits in one of 3 filaments which are arcing away from the Scorpius-Centaurus association. The movement of the Sun makes it appear like these filaments are ripples moving outwards. The filaments seem to be aligned with the galactic center. As we move further out, we start to see some other important structures. The Sun is at the center of the diagram, and to the north, slightly off-axis, sits the Pleiades. Further out, you will also notice a faint blue band that forms an oval called the Gould Belt. This is a vast ring of stars which is slowly expanding, but seems to be gravitationally locked together. At the centre of all of this sits another really important structure called the local chimney. This structure is actually off-axis from the galactic plane, and this matches the offset of the Gould belt as well. At its narrowest it is 800 light years across, and it forms an hourglass shape that we should all be familiar with. Gould's belt does not appear to have formed through the shock waves created by a supernova, which lacks sufficient punch as evidence in the lack of similar structures created by past supernova. Such an explosion would have compressed the interstellar gas within a giant star-forming molecular cloud in all directions from the supernova. Moreover, astronomers have not been able to explain why the resulting structure would be tilted near 20 degrees from the galactic plane and protrude so much out of the galactic disk. While multiple supernovae have been proposed, the lack of similar structures in nearby spiral arms does not support such a scenario. Our galactic Birkeland current would follow a decaying sine wave pattern, and therefore could be angled at 20 degrees at this location. Could a Z-pinch have formed a long time ago centered on the Pleiades, which explosively created an expanding ring of stars? This event could have cleared out the local plasma, leaving what we see as the local chimney, which is oriented in the same plane as the Gould belt. Now notice that Taurus, the constellation, is pronounced in English much like Taurus, the shape, and Taurus is the constellation containing the Pleiades. Yet tracing the origin of the word back, you find that the constellation itself was named for the cluster itself, and that the original name of the Pleiades was Tauri. So the name actually goes with that centre. Nowadays, the Pleiades only happens to appear among those background stars. Again, in mythology, as well as some esoteric knowledge, the star Alcyone itself is the central sun, about which our sun orbits. One of the earliest names of that star literally means the central one, or central sun. So how does this all relate back to precession? First, let's examine the concept of a nested Birkeland current, or a Bessel function Birkeland current carrying multiple stars in different shells. In this concept, there would be a star stream running along a central axis. These are coloured blue. For now we will show this as a straight line, but in reality this in itself will twist around a larger structure. Wrapped around this would be a helical stream of stars, and these are the white ones. This is actually a twisted filament. Mapping the stars to each strand is a little harder to do as there are no stars at the central axis. We suspect that Sirius sits on the opposite filament, and this is why you might hear references to the fact that we orbit Sirius, or in a loose sense we orbit about a common axis, which then orbits around Arcturus, which in itself orbits around the Pleiades. The time it takes for us to complete one rotation of this helical path with Sirius is around 25,000 years. In other words, a precessional cycle. If we zoom out a little from this twisted pair, then we start to see it as a single filament. We know that there are stars in front and behind us on this filament, so let's examine these stars and see if we can map them out. For simplicity's sake, I'm not showing the twisting motion these stars would make along their own filament. Further out are what we will now call background stars. These are the ones in red. From our perspective, they do not move enough for us to be concerned about their motion. The important point to note here is that for each of the white stars, their distance to the central axis will be about the same. Clearly, if we pick one star, some may be a little ahead and some may be a little behind, but there is a certain radius that could be deduced if the separation between the furthest and the closest star was not too large. Each of the white stars is moving in a circular orbit around the central star stream. This means that they will appear to move against the background stars with a variety of motions depending on where they are in their circular path. So what would this motion look like from here on Earth? When we look out at the stars, the first thing you will notice is that the background stars are moving in an anti-clockwise direction. This motion is a combination of our filament twisting around as well as the double pair twisting around the Arcturus filament. Each rotation around our local pair takes around 25,000 years, and each rotation around Arcturus takes around 4 million years. and this is why we think that the Earth wobbles, when in fact it is our motion along the helical path. The 25,000 years maps to our precessional cycle. Add into this the motion around Arcturus, and you can now explain why the value of precession is changing over time. We are not travelling in a straight line. The second point to note is that the stars ahead of us, and also behind if we looked in that direction, do not move at the same rate as the background stars. Our assumption is that the background stars do not move, so what we see here with the white stars is that they seemingly defy precession and are moving against the background stars. These stars should have what they call a higher proper motion. This just means that they are moving against the background stars. It is important to remember that at the moment this proper motion is assumed to be a linear one, meaning that the stars can only travel in a straight line. If we examine this motion, you will see that there are three components to a star's motion, from our perspective. Its movement across, let's for now call this X, and its movement up and down, let's call it Y, and lastly whether the star is moving towards or away from us. Let's ignore this last one for a moment. If we examine this motion of the stars, we would expect the X and the Y components of its motion to change as it transcribes a circular path around this helical structure. This means that over time this proper motion would change depending on where it is in the path. When we examine the proper motion for these stars, we do indeed see that they have a higher proper motion compared to other stars, and that they also appear to have a random direction from where we look. If we also examine the central star stream, then you will also notice that this seems to have an additional component to its motion, meaning that these stars should have the highest proper motion compared to other stars. And when we examine our nearest stars, we do indeed find that Arcturus has a much higher proper motion compared to any other stars near it. When we examine the motion of these stars towards and away from us, called the radial velocity, we see that this velocity is much smaller than the Arcturus proper motion, and all seem to be around 10 km per second. The exceptions are Altair and Rasselhage. If we examine the distance to each of these stars, we see no overall pattern. You could argue that this could all just be random and a pure coincidence, but if we take one further step, you will see that we can eliminate this random chance fairly easily. If we were to change our location to the central star in the star stream, so Arcturus, then when we examine the star's motion, you will see something completely different. Looking at the radial velocity, we see most of these drop to almost zero, with the exception of Rasselhage and Precession. The proper motions also seem to be fairly similar, with a noted exception of Altair. When we examine the distances, something remarkable springs out. They are all around the same 11 to 12 parsecs from Arcturus. So what does this all mean? If we are correct and assume that the motion of our star's filament wraps around that of Arcturus, then we would expect all these stars to have a very similar radius. We would also expect them to have very little motion towards or away from this central star, and they should all have similar motions around this orbit, making their proper motions very similar. And this is exactly what we see. If I pick any other star to perform the same analysis on, you will see that this does not yield the same results. This is not random chance. Further detailed analysis of more stars will start to reveal the structure and the connections to other star filaments. So why do we have some exceptions? Part of the motion that is not as obvious is that each of these stars is part of a pair of filaments that twist around each other. This means that at some points they will appear to be moving away from Arcturus more, and at some points it would appear as if they are moving towards Arcturus. Again, at the moment this is assuming a simple straight line with a perfect helix wrapped around it. We already suspect that all these filaments wrap around other larger ones, which in turn wrap around one which is centered on the Pleiades. This means what we assume as a straight line is not, but actually arcs off in one direction. And it is in that fact that we must understand why the value of precession has been changing. Our motion is in a curved line rather than a straight line. We are also assuming that the flow of plasma along these filaments is uniform. But this may not in fact be the case. There may be areas where this accelerates and areas where this slows down. There is a lot more work to do to verify this and to map this further out and look into if it is possible to identify the twisting filament pairs and separate it from the data. So what does this mean our local stars actually look like? Here we see the central stream representing the Arcturus star stream. This does not actually look like this in reality, but is more to help you visualize the central axis and understand where Arcturus fits. It would sit in about the center of this stream. Right at the bottom we see Sirius, Altair and the Sun, and then moving further away we see Rasselhague and lastly Gemma. Now clearly this motion is vastly sped up, and each orbit represents 4 to 5 million years. This central stream will actually be twisting itself around the central axis of the Pleiades. Here each revolution would take around 26 million years. This time frame also seems to fit in with the mainstream hypothesis of a nemesis star which disrupts the Oort cloud every 26 million years, causing catastrophes on Earth. At the same time, the Pleiades stream, and equally ours, would be moving in an upward direction. As you can see, when you superimpose all of these motions, it can look like a random mess. But by slowly sorting through this data, we can start to see the pattern which reveals our true motion through the heavens. More remarkable than all of this is the fact that this knowledge seems to have been forgotten, but our ancestors encoded this in both myths and the constellations themselves. In other videos I will explore these concepts further and expand on the idea of what the ancients knew and what it means for our understanding of the universe. For now, I hope you've enjoyed this journey exploring what precession really is. As always, be brave, be curious, the truth is waiting for us. Until next time.